Hello students, welcome to Vasiversity. Today we're going to be doing the limit of a function, tangent, and velocity definition. Alright, so let's go ahead and start first with tangent and velocity. So the word tangent is essentially coming from a Latin word tangus, which meant touching. Okay, so thus a tangent to a curve is a line that touches the curve. Right, and so let's take a look at a few examples. Right, so we have example A and B here. So essentially, right, we have a circle and we have a tangent line which attaches the line at the single point, right? So this is a tangent, while this point right here would be an intersection, but the tangent would be the point. Okay, so for essentially the figure A, right, the tangent line is the intersects the circle once and only once. Okay? And for more complicated curves, the curve B, the two lines L and T passing through a point P on a curve, and the line L intersects C only once, but it certainly does not look like what we think of a tangent, right? Because it intersects twice. So we have to be careful, but we're going to be learning in calculus what it means to have a tangent line. Okay, so for example, let's take a look at our first example. So we want to find the following. We want to find the tangent line to the parabola at the point 1, 1. So the first thing we got to do is, well, the easiest thing that we can do is to draw the parabola. Right, so y equal to x squared is going to look like this. So we have that it's a parabola, we have a point 1, 1. So okay, so we got to have a tangent line, right, passing through that point. And we know that it should exist. Right, so we'll be able to find an equation of a tangent line as soon as we know the slope. Right, so the slope of the line. So remember, from algebra, we know how to find a slope of a line. And so we have 2 points, P and Q, right? So the slope M is going to be equal to x squared minus 1 over x minus 1. Okay, so I'm doing that purposely so we can evaluate as close as we can, right? So because we want to find a slope, so the further we go in a parabola, the less accurate our slope going to be. Right, so for instance, lat Q, we're going to evaluate at 1.5, right? If we plug in 1.5, it's going to be 2.25. Okay, so then the slope of PQ is going to be equal to 2.25 minus 1 divided by 1.5 minus 1. So that's equal to 1.25 over 0.5, and that's equal to 2.5. Okay, so essentially the slope here is 2.5. And remember, the definition of slope, the slope is rise over run. Okay, but let's go ahead and try to approach our slope closer and closer to the numbers, right? So let's try to approach it closer and closer to the actual numbers. So if we run down the table, right, so if x is equal to 2, we're going to have a slope 3, 1.5 is 2.5, 1.1 is 2.1, 1.01 is 2.01. So we can see that it's approaching 2, right? It approaches 2 when we are approaching 1 from essentially from the furthest distance, right? So if we're approaching this point, right, from here, right, we're approaching it from the right because we're approaching 1. We're still greater than 1, but we're approaching it, right? We can repeat the same thing, but with the left-hand side, right? The left-hand side, we would approach it like this. Okay, right? So same graph, but now we're approaching it from the left. So we have 0, 0.5, 0.9, and now we also approaching 2, but from the left, right? So this graph is going to be like this. Okay, we're approaching it from the left. So essentially, we say that the slope of a tangent line is the limit of the slopes of the secant lines, because this is a secant line. And we essentially going to express it like this. We're going to say that limit as point Q approaches point P, right? We're not saying that it's equal, it's always approaching, right, of the slope MPQ is going to eventually become the slope M. So in this case, P is 1, right? So what are we going to have? We're going to have that limit as x approaches 1 of x squared minus 1 over x minus 1. Right, and we find out, right, based on those graphs that we have and based on the values that we plugged in, that it should be equal to 2, right, as we approach. But meanwhile, the reason why it's the limit is because we cannot really plug in 1, right? Why? Because if we plug in 1, we're going to have a 0 over 0. So we have to do something else in order for us to work it out. And in order for us to work it out, we have to only use the limits, because limits, they not exactly equal to the thing. So we will be defining it today, a proper definition of limits. So, okay, let's take a look at the figures that we can draw based on the points, right, as the thing is approaching. So, okay, as we approach the Q, we're going to get something like this, right? We're going to have, if Q is really far, we are very off, right? Our tangent line is very off. But as Q approaches, the blue line converges to the red line, right? We cannot pass it, right? We're approaching it from the right and approaching it from the left. From the right, we're almost there, right? So if we approach really close, the line's going to match. Same thing here. We're approaching from the left, and eventually from the left, the line's going to get so close, it's going to actually match. So we will find for sure the slope. Okay? So the slope, essentially, the slope gives us instantaneous, right, values. So, if we think about velocity, if you watch the speedometer of a car as you drive, right, in the city, you see that speed doesn't stay the same, right? And because the velocity is not constant, and of course, what does the speedometer do? The speedometer actually measures your velocity at the given second. We call it instantaneous velocity. Okay, so let's think about this example right here. So we're gonna call it here. So here's gonna be example 3. So suppose that a ball is dropped from the upper observation deck of a CN tower in Toronto, which is 450 meters above the ground. Find the velocity of the ball after 5 seconds. Okay, so from physics, we do know that the position formula for a falling object is going to be gravity divided by 2 times time squared. Okay, so gravity for Earth is going to be 9.8 over 2 times t squared. So that's equal to 4.9 times t squared. So we're going to use that equation. Okay, but we can find a velocity. How do we find a velocity? It's going to be essentially the slope of this graph, right? This is a parabola, and we're working with parabolas. But to be specific, right, we have the change in position over the change of time, right? And so velocity, or to be more precise, we're going to have average velocity first. So average velocity, we will have it as the following. It's going to be change in position over change in time. Okay, so let's plug in. So we're gonna have the following picture. So s at 5.1 minus s at 5, right, divided by so 5.1 minus 5, right? So I took 0.1 second away from 5, right? Because we want to know exactly at 5 seconds, but we might not be able to. So let's see. We will have that this is equal to, right, let's plug in. So we're going to have 4.9 times 5.1 squared minus 4.9 times 5 squared, right, divided by 0.1. So that will give us 49.49 meters per second. Okay, and so, well, if we decide to make a more accurate approximation here, right, as we go closer and closer and closer to 5, we'll be able to find the instantaneous velocity, right, specifically at that second. So the average velocity, right, becomes, so if we start between 5 and 6, then 5.1, 5.05, 5.01, we become closer and closer to 49 meters per second. Right, and turns out that the exact velocity is going to be 49 per second. All right, and okay, so how do we actually compute it? Right, so let's give a little bit better formula here. So if we have, again, 2 points, so similar as we had in the previous example of the parabolas, right? If we decide to say, okay, well, we have the slope of the secant, and which is equal to the average velocity in this context of problem. And slope instantaneous velocity, right? This is average, this is instantaneous. Instantaneous is essentially saying that it's in exactly same point at a time. Okay, so essentially we can have an interval, right? An interval. So we're going to have a plus ah, right? A comma, and then we will have a plus ah, right? This is our x interval here. And essentially, our goal is for h to be as small as we can. Or in calculus, we're going to say that h approaches 0, right? It's not equal to 0, but it becomes smaller and smaller and smaller. And so as it becomes smaller and smaller and smaller, we want to be able to identify what the actual value is at this point, so specifically the slope. Okay, now let's go ahead and talk about limits. So we haven't yet discussed it, but let's go ahead and move on to officially defining a limit. So a limit of a function. Limit of a function, right? So we're doing only essentially one variable function here. So limit of a function is defined as the following. So let's talk about intuitive definition of it. So suppose f of x is defined when x is near the number a. So this means that f is defined in some open interval that contains a except possibly at a itself, right? Because during the limit, we are not equal to the point that we're trying to evaluate it. Okay, so we can write that limit as x approaches a of f of x is equal to L, right? So we read it as the limit of fx approaches a, x as x approaches a is equal to L. So if we can make the values of f of x arbitrarily close to L, as close as we like, essentially, by restricting x to be sufficiently close to a, or on either sides of a, but not equal to a, okay, then we can say that we do have a limit. Okay, so let's take a look at some examples, right? We already had one example as we were evaluating the x squared minus 1 over x minus 1, right? But let's take a look at this example. So here we're going to have example 4. So as we have f of t is equal to square root of t squared plus 9 minus 3 over t squared. So we want to find the limit, right? So limit as t approaches 0. So most of the time we choose the values, right? Or we want to evaluate at the values that is not obvious for us, right? Because if we plug in 0, we're going to be dividing by 0. And dividing by 0 in mathematics is not good. So here we are not essentially dividing it, we're approaching to 0, right? We're evaluating and seeing what the actual behavior might be around 0. Right? And it turns out that it's not always infinity. So for this case, right, we're going to limit as t approaches 0 of a square root of t squared plus 9 minus 3 all over t squared. Okay, so if we try to approach, right, 0 closer and closer and closer, well, what will happen is the following. We'll find the values, right? So as t is 1 plus or minus 1, so from both sides, right, plus or minus 0.5, 1, 0.01, right? So we're approaching essentially 1/6. So it turns out that indeed, if we're going to 0, approaching 0, that's going to be 1/6. Okay, perfect. And of course, as we go closer and closer and smaller, we will be able to see that it actually is going to 1/6. Okay, so a similar example, right? Similar example can be done for this problem. So let's take a look at example 5. So if you have f of x, which is equal to sine of x over x. So again, we're going to be evaluating it as limit of x approaching 0 of f of x. So that's going to be limit of x approaching 0 of sine of x over x. Okay, so this one is a famous example, very, very popular to use, because if we plug in 0, we're going to get 0 over 0, which is identified. So undefined, so we cannot find it. But here, right, if we start approaching it closer and closer and closer to 0, well, it turns out that this expression will be equal to 1, right? One of the very special limits, right? Special limits. So we can be evaluating it, and then limit will tell us that it's equal to 1, but it's not essentially defined, right, at 0. Okay, and sometimes, right, sometimes limits don't exist, right? Limits don't exist, and sometimes we have to do some more of the analysis for us to see. So an example of a limit that would not exist is if we say f of x is equal to 1 over x. And the reason why is because limit as x approaches 0 of 1 over x is not a good function, right? If we graph the function, it will be as following. So 1 over x is we have this part and then this part. So end it. So right. So as we go from this side right here, right, from this side, what happens? We're going to positive infinity. And as we go from this side, approaching 0, we're going to negative infinity. So those two limits are not equal, right? And because they're not equal, because we have one side to be positive infinity, the other side goes to negative infinity, this one does not exist. D and E, right, does not exist. So sometimes, even though it might be obvious for us, like, oh, you know, maybe it's actually this, it goes to infinity. Sometimes we have to make sure that both sides are actually agree. And so here we're going to be learning the new definition, which is a one-sided limit. So a one-sided limit we can write as x of x approaching a from negative, so that means from the left-hand limit, right? What would be the right-hand limit? You guessed it right. It would be a limit as x approaching a plus, right on top. Plus is on top. That would be the right-hand limit. But in our case, we say that the left-hand limit, so the left limit, the limit from the left of f of x as x approaches a, is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a with x being less than. Okay, so specifically being less, right? So for the x a plus, right, we would talk about being greater than, right? So x approaching a plus, x gotta be greater, right? Greater than a. So that's why it's a one-sided limit, because we only consider one side and then the other side. So the definition of the limit. So the limit, especially mathematically, is only exists, right? Only exists when both left and right hand side are agree on the value. So the full limit, right? Limit as x approaches a of f of x is equal to L exists if and only if the left limit exists and the right limit exists and they are equal. Okay, so let's take a look at an example here. Right, so we are given this graph. Right, this graph. So this graph is given to us of a function. And then what we want to do is we want to use this graph to state the values of the certain things that it's asking. So let's take a look. So when I use the graph of the function g and use it to state the values if they exist. So as the limit of x approaching 2 from the left, right? We are approaching 2 from the left. So okay, so here's this 2, right? X equal to 2, and this is our g of x. And we're approaching it from the left, meaning that we're approaching it from here. Okay, what value is it? This is 3. This is equal to 3. How about approaching it from the right? From the right, we're going this way. That's equal to 1. So does the limit exist? No, because this 2, a and b, are not equal, right? So this one does not exist. Okay, so we will literally say d and e. Okay, how about the other one? So approaching -5. So if we approach -5, right? -5, so 5 from the left, that's what I mean. We're gonna get 2, right? If I approach it from the right, we're also gonna get 2. And when we're approaching, limit approaches to 5, it's also gonna be 2, right? But the value of this function is different, right? This kind of functions, we're gonna be learning in the upcoming lesson, those functions are called not continuous, right? Because it essentially doesn't have continuity. It's not equal at that point, even if we try to forcefully evaluate it. Okay, now let's take a look at the following example. right? It's going to be example. So this was example 7. I'm going to call it example 8. Okay, so we want to find the limit as x approaches 0 of 1 over x squared. Okay, so this one is different than the one we looked at of 1 over x, because it's positive now, right? From both sides. So if we try to evaluate it numerically first, right? So plug in some values, right? Both positive and negative. It all grows, right? It's symmetric. It's symmetric about the x-axis. So we grow to 1,000,000, so it keeps growing and growing and growing. So we will never stop growing, right? And the graph of such function, right, will be as following. So we can graph it, and it's going to look like this. Okay, so we clearly are approaching infinity, right? And specifically positive infinity. So that means both limits, right? Both limits. As x approaches 0, we're going to be approaching positive infinity. So the limit does exist, right? Because the left-hand side and the right-hand side limit will actually agree on each other, and therefore will give us the final value of positive infinity. So let's give a more intuitive definition of the infinite limit. Okay, so intuitive definition of the infinite limit is, well, let f be a function defined on both sides of a, except possibly at a itself, as always. Then, limit of x approaches a of f of x is equal to infinity means that the values of f of x can be made arbitrarily large as we please, by taking x sufficiently close to a, but not equal to a. Okay? And then, same thing, right, very similar definition we can give to the function that is approaches to negative infinity. Right? So again, let the f be the function defined on both sides of a, but not at a, and limit of x approaches a of f of x is equal to negative infinity. Means that the value of f(x) can be made arbitrarily large in a negative way by taking x sufficiently close to a, but not equal to a. Okay, so what would we have? What would we have? So an example would be of a function, which was, this one was 1 over x squared. This one can be negative 1 over x. I'm just going to put a negative in front of it, and now it approaches negative infinity. Okay, so now, sometimes, right, we can test things as essentially vertical asymptotes, right? So vertical asymptotes for some graphs can look like following. Okay, because infinity gives us vertical asymptotes. If you remember from rational functions, this is what we can have. Okay, so this is an example of the right-hand side limits and left-hand side limits. So let's define a vertical line. So a vertical line, right, is essentially a vertical line at point A. So a vertical line, x equal to a, right? So that's how we graph vertical lines on the x and y axis. So it's called a vertical asymptote of the curve. So asymptote means that we are approaching it, but never equal to that line, right? Or at least we're not intersecting that line or crossing it. So the vertical asymptote of a curve y equal to f of x is if at least one of the following statements is true, right? So one of the statements that are below, one of the 6 is true, then we have an asymptote. Okay, so as an example, right, example 9. So we can take a look at the following. So if we have this, we want to try it from left and right, right? And we will have that this kind of function will look like this. Okay, so x is equal to 3, and that's our asymptote, right? So the line x equal to 3 will be our asymptote. And of course, there are some periodic functions, right? Like, for example, graph of the tangent, right? Tangent of x. So if we decide to find the vertical asymptotes of tangent of x, we have to remember that what's tangent of x equal to? Tangent of x is equal to sine of x over cosine of x. Okay, sine of x over cosine of x. So that means all of our asymptotes are going to occur when cosine is equal to 0. Right, and so when does cosine equal to 0? At pi over 2, right, plus pi. So it's going to be period of pi here. So period of, we are going to be periodically, so every pi we're going to be at 0. So essentially, that's what we're going to have for the tangent, right? So essentially the lines of pi over 2 plus n pi, right? So every pi we're going to be moving through an asymptote. So of course we're going to have an infinitely many asymptote. Okay, And of course, we can do logarithms as well. Logarithms would have the negative effects. All right, perfect. So that would be it for today's lesson. Right. Next lesson, we're going to talk about how we actually treat the limits and how we would calculate limits and by using the limits law. And then we also will talk about the precise mathematical definition of the limit and not intuitive definitions. Intuitively, we can see through algebra how we can actually come across the limits. But next lesson, we will actually dive deeper into the mathematical aspect of the limit. Thank you and see you next time.